As we continue with discrete Markov chains, we'll be looking at heating times in this video. Um, we talk about the whole Markov chain thing. It's all about moving from one place to another. So now we look at heating times, which can also be referred to as first passage time. So this lesson introduces heating times, a fundamental concept in stochastic processes. And very simply, heating time answers the question, when does a stochastic process first reach a given state? So the first time a stochastic process first reaches a given state. So we'll cover things like definitions, discrete random walk examples, recurrence equations, Markov chain formulation, and Python simulations. So first of all, we talk about definition of heating time. So let X sub t be a stochastic process and A a set of states. So the heating time of A is TA, which is the infimum of t greater than or equal to 0. So from time t equals 0 upwards, such that x of t belongs to the set of states, right? So where TA is a random variable and it represents the first time the process enters A. So the first time the process enters a particular state, or a set of states, that is when you call the heating time. So you have a special case that for a single state A, so if you have a single state, so you have T sub small a, which is equal to the infimum, that's the smallest time. Infimum means the smallest time. The infimum of t greater than or equal to 0 such that xt is equal to A. So by intuition, we mean that heating times arise in many contexts, like random walk reaching a boundary, stock price hitting a level, Markov chain reaching a goal state. We are asking how long does it take to reach a target for the first time? Okay, maybe you are watching a stock and then you want to see the first time. Maybe you bought a penny stock and you want to see how the first time the stock hits like $15. Maybe you bought it for like $1.50, and then at some point you're watching the first time it hits $15 or something like that. So that's the idea of hitting time. So how long it takes to reach a target for the first time. Then we go on to talk about the idea of a simple random walk. Consider a random walk where x naught is 0, that's the initial state. At each step, you move +1 with probability 0.5 and move -1 with probability 0.5. So this is a simple uh, symmetric random walk because there's equal probability of moving +1 or moving -1. That's moving right or moving left. So define the heating time at T3 to be the infimum of n greater than or equal to 0 such that xn is equal to 3, right? So we then want to compute the expected value of this T3. So that's like the heating time for a simple random walk. So in this case now, we have the first step analysis. Let u of x be the expected time to hit target starting at x. Then we say that u of x is 1 plus half u into x plus 1 plus half u into x minus 1. Okay, so this is because one step is taken and the cost of that one step is 1. Then the process continues from a neighboring state like that. So, and then we can have a model to look at that. So the finite model for a gambler's ring now. So imagine we have state 0, 1, 2, 3. So because we are taking 3 steps as we saw up there. So 0, 1, 2, 3. So the target is 3. So absorbing states, we have absorbing states 0 and 3. Okay, so u of 0 is 0 and u of 3 is also 0. So this we can set this as boundary conditions. So from the equations now, we can say u of 1, u of x is generally this. So u of 1 will now have to be 1 plus half u of 0 plus u of 2, because now because u of 1, this is going to be u of 2, half u of 2 plus half u of 0, and that's why the half has been factorized out here. So we have 1 plus half into u of 0 plus u of 2. Then for u of 2 now, we have we have set 0 and 3 as boundaries, so we are moving from, so we are now focusing on u1 and 2. So for 2 now, we have 1 plus, so if you put 2 here, 1 plus half u3 plus half u1, right? So that means u of 2 is 1 plus half u1 plus u3. So if you then solve the system, so you have so this is u1 equals 1 plus half u of 0 plus u of 2. So you can see like terms here now. So if you solve the system like a simultaneous equation, you're going to get u of 1 to be equal to 1 plus u of 2 divided by 2, or half u of 2. And u of 2 is going to be 1 plus half of u of 1. So if you solve this simultaneously, because u of 1 is here, u of 2 is here. So you can then solve u of 1 and u of 2 in terms of u of 2 and yeah, in terms of U of 2 like that and U of 3 possibly. So so you have all of this. So if you plug into first equation, then you can finally have that U of 1 is 1 plus half into 1 plus U of 1 into 2. And if you simplify all of that, you get U of 1 to be equal to 2. So it means that the expected time will be 2. So that's like the heating time. And if you try to work that out around using Python code, you see the result is like 1.98 blah blah blah, and 1.98 to one decimal place is 2, to two decimal places is also okay, that'll be 1.99. So to one to nearest whole number, that's 2, one decimal place, it's also 2, like that. So that works with this ET equals 2 that we got right here. So then we'll talk about a continuous time example, talking about Brownian motion. So let B sub t be Brownian motion. Then we define the heating time T of A equals the smallest time, infimum time greater than or equal to 0, such that BT is equal to A. So the key result here is that the expected value of TA is infinite. Although Brownian motion will hit any point, the expected heating time is infinite. So for Brownian motion, expected heating time is not defined. It goes on forever and ever. Then we have general method to compute heating times. So step one, define U of X equals expected time of expected time of expectation of T given X naught equals X, right? So step two, write recurrence. U of X equals 1 plus summation over Y of P of X comma Y U of Y. Then step three, apply boundary conditions, target state U is 0, and solve the linear system, just like the situation that we have here, for instance, okay, because it's coming from this is like the general model we are following. So you have U of X 1 plus half U X plus 1 half plus half U X minus 1, and we set 0 and 3 as boundary conditions because they are absorbing states. And then we look at this one in between, and then we try to solve for U1 and U2 that we are looking for. Okay, so so finally we have U1 to be 2. U1 is 2, and if U1 is 2, then U2 is just U2. U1 is 2, right? So we have that. So that's the shortest time it's going to take, I believe. So that's why we stop at 2 there. So we have Markov chain formulation. So let P be the transition matrix. Define HI to be expected time to hit target G given X naught is equal to I. Then HI is 1 plus summation for K not equal to J of PIK HK. And then we have the Python code, linear algebra solution. Imagine you have 0, 0 0.5, 0 0.50, 0 0.50, 0 0.50, 0 0.50, 0 0.5, and all of that. So you run that and you get what you should get here, talking about Markov chain formulation there. So you have 6640. So in all, we have these key properties. We have non-negativity for the heating time. TA is always greater than or equal to 0. You can't have negative time, by the way. Then you have you have it as a random variable. TA is a random variable, and it can be finite in the sense that it can be infinite, I mean, so that the expected value of TA is equal to infinity in some cases. So like in Brownian motion, then it depends on starting state. So expected value of TA given X naught equals X. So we have applications of this in gambling problems, stock price thresholds, reinforcement learning, network systems, and of course, population dynamics. So in summary, we have that heating time measures first time a process reaches a target, and the key tools are recurrence equations, Markov chains, linear algebra simulation, and they are central to probability theory and stochastic processes. So that takes us to some practice problems. Solve the following problems. Show all steps where appropriate. A symmetric random walk starts at x not equals 0. Find the expected heating time of state 2, you know. Find the expected heating time of state 2. Then I think we already did this symmetric walk thing the other time. Of course, the expected okay, the expected value of the random walk is always zero, right? But hitting time is different. Then boundary hitting. A random walk starts at x not equals 1 with absorbing states at 0 and 3. Find the expected time to hit either boundary. Okay, I think it's like the other one we did the other time. So, and then we have biased random walk at each step. So a random walk is biased if the probability of reaching, if the move +1 and -1 have different probabilities, but if they have the same probability, we say they are simple symmetric random walks. Then probability versus step for a symmetric random walk starting at 1, complete probability of hitting 3 before 0. Then expected time to absorption is another thing we want to compute. So you want to check all of that out. Then small Markov chain, given transition matrix P equals this, find expected hitting time to state 2, starting from state 0. Then we have a recurrence setup. So try your hands on all of this. Let's see how well it all goes. So we have, I think that was the system we had the other time. So trying to solve this, I think you get the same result. Then expected steps with drift. If P is greater than 0, does heating time to a positive state increase or decrease? Then you have multiple target. Define the heating time of a set. How does this change the recurrence? Then heating probability versus time. So try your hand on this. Let's see how well it goes. If there's anyone that is problematic, you can let me know in the comment section, so I can maybe probably make another video to explain them. So try your hands on this and let's see how it goes. Let me know how helpful this is for you. And if there's something else let me to try out, feel very free to let me know. Um, if you have subscribed already, I thank you very much for doing that. And if you haven't subscribed, why not go ahead right now, subscribe and hit the notification bell so you can always get alerted each time a new video is released. Then if you don't mind, you can become a member of the channel by clicking on join. That gives you special privileges like seeing some videos first before other people see them, or being the only one seeing certain videos because you're a member of the channel. You could also request for PDF copies of my notes with which I teach. You can you can we can hang out together to discuss whatever interests you in my channel, be it mathematics, data analysis, data science, machine learning, scholarships, whatever. So you can make yourself you can avail yourself such opportunities. So ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.